Well, welcome everybody, welcome. Thank you very much for coming along on this blustery Tuesday day to hear about Isaac Newton and some of his laws. And essentially today's talk's really going to be quite geometric because I'm going to look at the most important work really that Newton produced, which was his Principia, in which he a magnificent book in which he proved his universal law of gravitation and his laws of motion. But first of all, I want to give an overview of Isaac Newton's particularly rich, complicated and successful life. And not only in the Principia did he prove his law of universal gravitation, but he also showed how two bodies would move, the orbit of two bodies moving under mutual gravitational attraction. He was able to describe the orbits completely. And that, of course, gives rise to the natural question of trying to explain the motion of more than two bodies under gravitational attraction. And many people tried that over the next couple of hundred years. And I want to look at the endeavours of one particular mathematician, Henri Poincaré, who took a geometrical approach to try to find the motion of three bodies, a simplified case of three bodies moving under gravitational attraction. That's what I mean by it's sort of quite a lot of geometry in today's talk. And finally, I'm going to look at the question as to whether or not the solar system is stable. So if you thought you were coming along for a triviality, you're not. We're going to deal with a very important question, and you can amuse and astound your friends with the answer as to whether or not the solar system is stable. So you have to stay to the end in order to get the answer to that. Well, in his time, Newton was exceptional, very exceptional, in the extraordinary rapidity with which success came his way. By comparison, Galileo ended his days persecuted by the Inquisition. René Descartes died in exile in Stockholm, surrounded by hostile scientists and an unfriendly doctor, while Gottfried Leibniz died largely forgotten, and with, we are told, his secretary as his only mourner. In contrast, in April 1727, the French writer and philosopher Voltaire viewed with astonishment the preparations for the funeral of Sir Isaac Newton. The late president of the Royal Society lay in state in Westminster Abbey for the week preceding its funeral. At the ceremony, his coffin was borne by two dukes, three earls, and the Lord Chancellor. He was buried, Voltaire observed, like a king who has done well by his subjects. No scientist before or since has been so revered. Few such have been buried with such dignity and high honour. The boy from rural Lincolnshire had come far. The quotation at the bottom of the slide is from Alexander Pope and written shortly after Newton's death. It shows the reverence that Newton's contemporaries felt towards him, and in particular for his work on gravitation. Nature and nature's laws lay hid in night. God said, "Let Newton be," and all was light. In the words of the French physicist and mathematician Laplace, since there's only one universe, it could be given to only one person to discover its fundamental law, the universal law of gravitation. And that's what Newton did in his Principia Mathematicae, one of the greatest books of all time. Newton's interests were not confined to mathematics, and I can illustrate some of those by looking at his tomb in Westminster Abbey. It was designed by William Kent and erected in 1731, and its rich symbolism alludes to some of the fields of Newton's interests. On the left is a picture of the memorial, and on the right, an engraving. The base bears a Latin inscription and supports a sarcophagus with large scroll feet and a relief panel. And let me read a translation of the inscription. It's in Latin and can be translated as follows. Here is buried Isaac Newton, knight, who by a strength of mind almost divine and mathematical principles peculiarly his own, explored the course and figures of the planets, the paths of comets, the tides of the sea, the dissimilarities and rays of light, and what no other scholar has previously imagined, the properties of the colours thus produced. Diligent, sagacious and faithful in his expositions of nature, antiquity and the Holy Scriptures, he vindicated by his philosophy the majesty of God, mighty and good, and expressed the simplicity of the gospel in his manners. Mortals rejoice that there has existed such and so great an ornament to the human race. And we can also see something about his range of influence, range of activities, if we look at the Sarcophagus. And it depicts boys using instruments related to Newton's mathematical and optical work, including the telescope and the prism, and his activity as master of the mint. The boys playing on the left are playing with his reflecting telescope. On the right, we have a furnace with newly minted coins. That's alluding to his time as warden and master of the mint. On the middle here, there is one boy who's weighing the universe, which is what we are able to do to find the relative masses of the different planets. There's the sun, and hanging down here are all the other planets in the solar system. And then on the right, just to the right of it, there's another boy playing with a prism and Newton's discovery that white light is a mixture of colours. Right. Above the sarcophagus, going back, this is why I used the sketch, because it's a little bit clearer there, is a reclining figure of Newton in classical costume, his right elbow resting on several books representing his great works, his works in mathematics, the Principia and celestial dynamics, in optics, and also on divinity and chronology. On the background, there's a pyramid on which there's a celestial globe with the signs of the zodiac, the constellations, and the path of the comet of 1680. Comets were quite important in the story I'm going to tell later on. On the top of the globe sits a figure of astronomy leaning upon a book. So let me briefly now outline Newton's life. It took place against a backdrop of only 3 locations: Lincolnshire, Cambridge, and London. The man who's very famous for comparing himself with a boy playing with pebbles on the beach, not noticing the ocean of truth out before him, Newton is unlikely ever to have seen the sea. He was born Christmas Day 1642, and that's old style by the Julian calendar, in force in England. For the rest of Europe, using the modern Gregorian calendar, the date was the 4th of January 1643. His father was an illiterate but fairly prosperous yeoman, and he died 3 months before Newton was born. Newton's mother remarried when he was 3, and for the next 8 years, Newton lived with his grandmother apart from his mother. And all Newton's recent biographers have seen this separation from his mother between the ages of 3 and 10 as crucial in helping to form the suspicious, tortured, and neurotic personality of the adult Isaac Newton. The mother and son were together for only a few years before he came to the free grammar school in Grantham, 7 miles away. And we know little about the type of education he would have received, but he would have learned mainly Latin grammar. That's what grammar schools were for, and more than a modicum of basic arithmetic. And in later years, many stories of Sir Isaac Newton's school days were put about, not least by Sir Isaac Newton himself, telling of his mechanical inventiveness, his experimental ingenuity, and his uneasy relations with his fellow pupils. And he tells the story of making a small windmill that actually ground flour, powered by a mouse. And in later life, he was to make the equipment for his experiments. For example, he made the equipment that enabled him to grind his own lenses for his optics experiments. As Newton himself remarked, "If I'd stayed for other people to make my tools and other things for me, I had never made anything of it." 17, it was time for him to return home and manage the estate, and apparently this was a total failure. His mind was full of problems, full of things he wanted to think about, and he had no interest in earthly matters in hand. And the story's told, probably apocryphal, that he was leading a horse up a hill and the horse slipped its bridle and he went on leading the bridle up the hill. Well, anyway, for this and other reasons, he was sent to Trinity College, Cambridge, which he joined in 1661, and which became his home for most of the next 35 years. To begin with, he was a subsizar, rather strangely, because his mother was really quite wealthy by this time, meaning that he earned his keep by serving the fellows and wealthier students, cleaning their boots, waiting at table, and emptying their chamber pots. Newton was essentially self-taught at university by his own self-directed reading. And early in 1655, He became a Bachelor of Arts, but that was just because he'd been up at university for 4 years. It was a formality. The more crucial milestone was passed the year before, when he was elected a Scholar of Trinity. And somewhat surprisingly, because there was no evidence then of any distinction. But anyway, his position was now guaranteed for another 4 years, and his duty as a subsizar ceased. Then, in the summer of 1665, the dreaded plague reached Cambridge, and the university closed down. This was the last widespread outbreak of bubonic plague in England. Newton returned to Lincolnshire, where he spent most of the next 2 years until the spring of 1667. And we have Newton's account, written over 50 years later, of his investigations during those 2 years. And I'm going to share that with you. Don't worry about the details. Just get a feeling for the range and extent of his successes. Some of the points that he makes, I'll come back to later. So, this is his account of the 2 plague years when he was on his own back in Lincolnshire. In the beginning of the year 1665, I found the method of approximating series and the rule for reducing any dignity of any binomial into such a series. I'll show you an example shortly. The same year in May, I found the method of tangents of Gregory and Slusius, and in November had the direct method of fluxions, and the next year in January had the theory of colours, and in May following I had entrance into the inverse method of fluxions, what we would now call differentiation and integration. And the same year, I began to think of gravity extending to the orb of the moon, and deduced that the forces which keep the planets in their orbs must be reciprocally as the squares of their distances from the centres about which they revolve, the universal law of gravitation, and thereby compared the force requisite to keep the moon in her orb with the force of gravity at the surface of the earth, and found them answer pretty nearly. And all this was in the 2 plague years of 65 to 66. For in those days I was in the prime of my age for invention, and minded mathematics and philosophy more than at any time since. Well, of course, it's now impossible to exactly corroborate these details, but the spirit of the account seems right. In an extraordinary short time of 2 years, Newton laid the foundations of celestial dynamics, optics, and mathematics. And let me show you one of his manuscript pages from this period, from 1665. He had quite a neat hand. And what he is doing here is he's calculating the area under this shape, this curve, which is a hyperbola, and the areas under this curve, the hyperbola, are in fact calculating logarithms. And he's calculating a logarithm, an area under the curve, to 55 decimal places. So if you're going to do it correctly. And let me show you how he does it, because this is a very powerful technique. I'm going to zoom in on line 3, down here, up there, I mean. And if you look at line 3, on the left-hand side, you have an expression which gives you the area of the, which is the hyperbola, the equation for the hyperbola. It's a squared, he writes that as a times a over a plus x. And what he does, and you can do it using, if you know about geometric progressions, is he writes this out as an infinite series. All right? So it's like a polynomial, if you know about them, but it keeps going on forever. There's the etc. down here. So he's taken an expression and he's written it out as an infinite series, a series of other terms. But the thing is, these other terms only involve powers of x. And he knows how to find the area under a curve, which is given by a power of x. He knows how to integrate powers of x. He sort of says it here, multiplied by x and divide. Therefore, multiplied by x and divided by the number of its dimension, which you may remember. So to integrate a power of x, x to the 5 becomes x to the power of 6 over 6. So he is now able to do the integration of these things term by term, is what we do. So he had a complicated expression. He writes it out as an infinite series in simpler things. He's able to do something to each of those simpler things, and then he adds them up, which is why he goes to the 55 decimal places. And the reference to the binomial theorem earlier on during the plague years gave him another technique of being able to write certain expressions out in terms of infinite series, and he was able to apply this technique to them. All right. And I've said it was the same year he had the binomial theorem. And it's also during this period that the story of Newton and the apple originated. And we've got two sources for that. One of them was his niece who looked after him in later years, and the other the 18th century royal astronomer royal, James Bradley, who had known Newton personally. And there, of course, the whole point of the apple story is that seeing an apple fall, Newton realised that the force that draws the apple to the Earth is the same universal force that keeps the moon in orbit around the Earth and the planets in orbit around the sun. And although his main writings about this were not to appear until the Principia in 1687, the initial ideas came from these plague years. Right, so let's continue on with the brief biography. University of Cambridge reopened in 1667 and Newton returned to Trinity College soon after. That autumn he was elected to a fellowship of the college, and 2 years later he became, at the age of only 26, Lucasian Professor of Mathematics, the position he held for the next 32 years. Now, the first optical work of Newton to become widely known was not his theoretical inquiries into the nature of colours, but his reflecting telescope, and it caused an absolute sensation when it arrived in London in late 1672 and ensured Newton's election to the Royal Society. Newton, as I mentioned before, great manual skills, and constructed the telescope himself, grinding the mirrors and making the tools necessary for that as well. And those skills came in very useful for another activity that he was spending a lot of time on, his work in alchemy and in chemistry. And as the decade went on, he was getting more and more interested in theology as well. And the 1680s is the decade in which the Principia appeared, the decade in which Edmund Halley invaded the Cambridge lair of the sleeping giant and squeezed the work out of its reluctant author. A world that was beginning to forget about Isaac Newton, except in select scientific circles, awoke to find the world changed by him. And almost from the moment of its publication, even those who refused to accept its central concept of action at a distance recognised the Principia as an epoch-making book and gave its author an international reputation. And you can understand why people didn't want to accept action at a distance. People were trying to get rid of the magic and the mystery out of science and mathematics, and here was somebody explaining motion by means of a force for which there was no carrier. Unlike Descartes' theory of planetary motion, where the planets were swept around by vortices, which seems much more reasonable if you think of the way the leaves outside are being blown about in the wind. But one of the things Newton did in the Principia was to demolish Descartes' vortex theory. So at the end of the decade, Newton continued his transformation to a public figure by providing the backbone to the university in its rejection of King James II's demand that a Benedictine monk should be admitted to the degree of Master of Arts without the appropriate exercises and oaths. And this resulted in his election in 1689 as a Member of Parliament for Cambridge. And he seems to have enjoyed his time in London. And that was one strand in why he decided to leave Cambridge. The other relates to the mental breakdown he suffered in 1693. And there have been a lot of explanations given for this. Most common one I've read has that it was due to mercury poisoning, and I think analysis of his hair, some of you may know better than me, did show that there was mercury in his body. But I think it was more due to overwork and disillusionment. In the early 1690s, what he was trying to do was to weave together his interests in a whole variety of areas: mathematics, dynamics, optics, alchemy, and theology, and try to bring them into a coherent framework. But by 1693, he had withdrawn his theological publications. He had scuttled plans to publish works of mathematics and optics, and hesitated over plans for a second edition of the Principia. He also reached a climax of disillusionment in his alchemical researches in the summer of 1693. 1693 probably was the summit of his intellectual activity, and apart from some work he did after that on lunar theory, he didn't inaugurate any new investigation of importance. And he devoted the remaining years of his life to reworking the results of earlier endeavours and became Warden of the Mint in 1696. And the last 30 years of his life are where the secretive, retiring scholar became an influential public figure, attaining and ruthlessly wielding power. He first put the Mint to rights. And Newton, who could do nothing half-heartedly, took charge of the recoinage which was needed to stabilise the monetary crisis in the economy. He was an extraordinarily efficient administrator and a shrewd political operator. And he acquired power and influence until 1700 he became master of the mint. In his early years in London, Newton paid little attention to the Royal Society, which was going through an unhappy and directionless phase. But then in 1703, in March of 1703, Robert Hooke died, and Robert Hooke was a major irritant to Newton because he had criticised Newton about his theory of colours and had also laid claim to the inverse square law that appears in the Universal Law of Gravitation. But public recognition was coming thick and fast. So, for example, in 1705, he was knighted by Queen Anne. And when he eventually died in his 85th year, it was a signal for a display of pomp and pageantry and a wealth of poems, statues, medallions, and other communications. So after this brief biographical sketch, let me go on to some of his laws, Newton's laws, essentially those contained in his mathematical principles of natural philosophy. And as I've said, it was Edmund Halley, of Halley's Comet fame, who visited Cambridge and coaxed and cajoled Newton to publish the Principia. In fact, Halley even paid for the work to be published. Well, when visiting, Halley asked Newton what he thought the curve would be that would be described by the planets, supposing the force of attraction towards the sun to be reciprocal to the square of their distance from it. Sir Isaac replied immediately that it would be an ellipsis. The doctor, struck with joy and amazement, asked him how he knew it. Why, saith he, I have calculated it. Whereupon Dr. Halley asked him for his calculation without any further delay. Sir Isaac looked among his papers but could not find it, but he promised him to renew it and then to send it to him. And in fulfilling this promise, Newton eventually wrote the Principia. And the title is Latin for Mathematical Principles of Natural Philosophy. And the book is about a mathematical investigation of the forces and the motion of bodies both on earth and in the heavens. Newton was the first person to unify terrestrial and celestial mechanics. His approach in the Principia does not use calculus. He uses geometry and proportion, with forces, velocities, accelerations, distances and times, all represented by lines and areas. And I want to convince you of that when we look at one of the propositions in the Principia, the core proposition. But first of all, he started with his 3 laws of motion. And the first one is relatively straightforward. If you do nothing, nothing changes. But there is content to the first law because it says that what a force does is a force produces a change in motion. So that if something is moving uniformly and no force is acting on it, it continues to move uniformly. If the body is still stationary and no force acts upon it, then it stays where it is. The second law gives you a relationship between force and change of motion. Forces produce change of motion. And it's a proportionality. If you double the force, then you double the change in motion that is produced. Doubling the force doubles the acceleration. And then the third one, which you probably got through a study of collisions, saying that to any action there is an equal and opposite reaction. And Newton's cradle was a device that constructed to illustrate the third law following a hint in the Principia. And from the web here, and I think it's still surprising when I see it, you lift one of the balls on the side and let it drop down, and instead of the other 4 moving out, what happens is that the one on the other side jumps out, and that's because the first one comes down, hits the next one, and when it hits it, it stops. The next one moves along, hits the one beside it and stops. The next one moves along, hits the one beside it, stops. And then the last one has got nothing to stop it, so it swings out. So using the action reaction. And here's a different take on it here, which I might try with my 5 grandchildren at Christmas if their parents allow me. But I doubt it. All right, so now we know about forces and changes in motion. What we want to do is to get a force. And the force we're going to get is the Universal Law of Gravitation. And this law states that the gravitational attraction between two masses varies directly as the product of the masses, as their sizes, and inversely as the square of the distance separating them. So everybody in this lecture theatre is attracting each other gravitationally, and between me and you, if we were to move twice as far away, the gravitational attraction would drop by a quarter. If we were to move 3 times further, it would drop by a ninth. So it goes down as the square of the distance, inversely as the square of the distance. And it's gravitational attraction that causes objects such as apples to fall to the earth and also explains the moon. And let me show you this, if I may, to explain the motion of the moon, which is a book published, in fact, 1728 after Newton died, but he was working on. It's a simpler version of his book 3 of the Principia. It's called a Treatise of the System of the World, and it contains this diagram on the right-hand side, and the whole book is available. I've given a source where you can get it there, and it's quite accessible. All right, so let me just blow up that diagram a little bit more. So what we want to do is to show that the motion of the moon can be explained in a similar way to the motion of an apple on Earth. And what we're going to imagine is that we have a mountain up here, V, and we're at the top of a mountain, and we're going to throw an object from that top of the mountain horizontally. And we throw it and we're going to throw it with increasing speeds. So first of all, we throw it, and of course it falls to Earth, and it ends up at D. All right, then we throw it a little bit faster, and it still falls to Earth, and it ends up at E. Then we throw it a little faster, and it falls to Earth, but this time it's gone further, and it ends up at F. Then we throw it a little faster again, and then it's falling to Earth, and it ends up, I think that's G. Yes, should be, shouldn't it? F, G. Then we throw it just a little bit faster, and it falls to Earth again, but the Earth is curving away from it at the same rate that it is falling, so it comes right round back to where it started again, and assuming there are no retarding forces or resisting forces, it will go round again. But it's just a limit of the same behaviour of things falling to Earth. So the motion of the moon, caused by the same gravitational force, if we imagine the moon going round here, can be explained by the same gravitational force as apples falling to Earth. And Newton then, of course, did the calculation with the inverse square law and showed that the numbers are correct, that the rate of fall of the moon is given by what it should be, given it's that much further away than something falling on the surface of the Earth. But you can see qualitatively why it is the case that the gravitation explains the motion of the moon. All right. So let's do a little bit of geometry then, and what we're going to do is to show you how Newton used Kepler's second law. Now, Kepler's second law, this was derived experimentally from astronomical observations. And what Kepler found was that if you've got a planet going round the sun, let's say, something that is orbiting, and you draw a line from that planet, an imaginary line from that planet to the sun, and you look at the areas that that line sweeps out, then in equal times it's going to sweep out equal areas. So it's a quantitative way, really, of saying that a planet moves faster when nearer the sun than it does when further away from the sun. So I'm saying here that these 3 areas, this one, and this one, and this one, are all equal. Equal areas in equal times. And you can see why that tells you that the planet is going faster here. Because if in 1 minute it has to sweep out the same area because it's closer to the sun, it means that this curved part has to be longer than when it's over here. In other words, it's going faster in that minute. What Newton did in the Principia was to prove this result for a force like this between a planet and something like the sun. And let me just show it to you, and then I'll try to explain what it means. Right. So this is Book 1, Proposition 1, Theorem 1. This just comes after the 3 laws that I've already shared with you. And let me show you what it means. Let me go to the diagram down here. All right. The orbit is, and I'll say more about the orbit in a minute, the planet is going from A to B, B to C, C to D, D to E, E to F. Right? And it's moving under an attractive force towards this S here. So the force is an attraction towards S. Now, what Newton's Theorem 1, Proposition 1 of Book 1 says is that the following areas are going to be the same. Equal areas in equal time. So divide your time up into equal parts, let's say a minute or a second or whatever. And then in the first minute, the particle goes from A to B, and therefore we have this area SAB. In the second minute, the planet goes from B to C, and what we're saying is that the area SAB, the first area, first red triangle, is equal to this one, SBC. And then in the next minute, it goes from C to D, and we're saying that the same area is swept out so that the two previous areas are also equal to SCD. And you're getting the pattern by now. In the next minute, it goes from D to E, and we're asserting that this triangle here has got the same area as the previous three. And then the last thing on this diagram, it goes from E to F, and therefore that area, SEF, is the same as the previous ones. Okay. Now, let me explain the strange thing about the orbit, because this is where he's very, very clever. What he asserts is that in a minute, the planet, where we're taking our equal time, goes from A to B. Then if it were left alone, in the next minute, it would go from capital B up to small c. But what he imagines is that at B, there's a tug, a gravitational tug, an attractive tug towards S, and the planet is diverted from its path, the straight line path that it would continue on by his first law, and instead of going from B up to small c, it goes from B up to capital C. Right? Then, if it had been left alone, it would continue on from capital C up to small d, but it gets another tug at C, which diverts it from going from C up to small d to C up to capital D. Right? And the same thing happens at D, the same thing happens at E, the same thing happens at F. So he's discretized time, and he has it gravitational tugs acting at B, C, D, E, and F, which is why the orbit is composed of those straight line segments. And as I say, what we want to do is to show that all of those triangles I coloured in a moment ago are equal, and the same, if I can show that the first two are equal, the same technique will work for the rest of them. So the two that I want to show equal are here, on the left, SAB, and here, SBC. And we're going to do it by the age-old technique of showing that each of them is equal to another triangle, the area of another triangle, and if two things are equal to the same thing, then they must be equal to each other. And I'm going to show that each of these red ones is equal to the green one. Right? So we've got the two red triangles down here, SAB, and then we've got SBC, and we're going to show that each of them is equal to the green triangle, SB small c, SB small c, and therefore they must be equal to each other. All right, so to do this, you should really turn your head on the side, but you would look very foolish doing that, so I'm just going to rotate. So this is here, taking the left-hand picture and rotating it so that this line here is horizontal. Right. So now, how can we show that the red and the green triangles have got the same area? Well, we've got a red and a green triangle. Their bases are the same. The red base here is the base of the red triangle. The green one line here is the base of the green triangle. They're equal because it's the distance the planet travels in a minute. And notice that the two triangles have got the same height. Their vertex is at the same point. Now, if you cast your minds back, you remember that the area of a triangle is half the base by the height. So these triangles have got the same base, they've both got the same height, so their areas are going to be the same. So that red triangle is equal to the green one. Now let's do the other one, and again I've rotated it, and this time the red one and the green triangle have got the same base, so that's half of it done already. And then if you look at the heights, well, the height of that one is up to capital C, and the height of that one is up to little c. And Newton can show, using his laws, that this line C to small c is parallel to the line SB. So here we have two triangles. They've both got the same base, and they both have the same height because their vertices lie on a line which is parallel to the base. So again, you've got the red triangle is the same as the green triangle. So let's just go back through it. We've now shown that red is equal to green, red is equal to green, and back here is telling us that those two areas are now going to be the same. And what Newton then does is he uses a limiting argument, and he imagines the time intervals to become smaller and smaller and smaller, increasing the number of triangles, as he says, ad infinitum. He ends up then getting a curved orbit, and the general result that the line joining the planet to the point at which the attraction occurs is going to sweep out equal areas in equal times. But you can see it's very much a geometric argument, and in actual fact it doesn't use very complicated geometry, just showing that what the area of a triangle is. It's the framework as how he went about to approach it that's so brilliant. And in fact, in the next proposition, he uses the same diagram, this diagram here, to prove the converse result, that if the line joining something which is orbiting to a fixed point sweeps out equal areas under equal times, then it's moving under an attraction to that point. So it's the converse. But what he now has is a way of representing time by a geometrical thing, by an area. Time is now represented by an area. And in Proposition 11, Problem 6, he answers the question, given the shape of the orbit, an ellipse, if something is orbiting in an ellipse, and the fixed centre towards which the force responsible for the shape of the orbit points, how does the magnitude of that force vary with the distance of that force from the centre? And the answer is the force must obey an inverse square law. If something is travelling in an ellipse under an attractive force towards a fixed point, then it has to be undergoing an attractive force, which is an inverse square law. And if you had a chance to look at what is happening here, what he is doing is he's trying to find out what the force is, which corresponds to finding out what the acceleration of the orbiting body is. But an acceleration is a change of motion. A change of motion he represents by the length of a line, a change of motion in a certain time. He represents the time by the area of one of those triangles. So all of this argument in here is trying to approximate or trying to say what the ratio is of a length of lines compared to the size of an area. No calculus, whatever, just using geometrical considerations in order to do it. And it's how he represents time that is at the basis of it. And he also showed in other parts of the Principia that if you've got two bodies moving around under gravitational attraction, they'll orbit in ellipses with about their mutual centre of gravity. So I want to leave Newton for a while and move on 200 years, because Newton solved the problem of two bodies moving under mutual gravitational attraction, and what I want to do now is to look at more than two bodies, at three bodies. All right, so 200 years later, 1889, King Oscar II of Sweden, who's an enthusiastic patron of mathematics, he offered a prize of 2,500 Swedish crowns for a memoir on any of four given topics, one of which was predicting the future motion of a system of bodies moving under mutual gravitational attraction. And this is what he's saying here. On the left-hand side, if you were to read it out, given a system of arbitrary many mass points that attract each other according to Newton's laws, under the assumption that no 2 points ever collide, try to find a representation of the coordinates of each point as a series and a variable that's some known function of time, and which converges, which gives you an answer. So find out what's happening in the future if you know the positions and the speed of the bodies at this present moment. All right. And the attempt on this problem by Henri Poincaré is very important, has been very important and influential. So let me tell you now about Poincaré, 1854 to 1912. And he's really viewed as one of the great geniuses of all time, probably being the last person to cover the whole range of mathematics, founded the theory of several complex variables and algebraic topology, and one of his problems in algebraic topology was only solved this century. It's one of the clay problems, the Poincaré conjecture. And Poincaré responded to King Oscar's challenge by tackling a special case of the problem when there are only three bodies. But not only are there only three bodies, he takes one of them to be an infinitesimal little dust particle, which he takes to have no gravitational effect upon the other two bodies, but is itself gravitationally influenced by the other two bodies. So you can see the cleverness trying to reduce the problem enough so you may be able to get a handle on it, but at the same time preserving some of the complexity of it. All right? And what he hoped is that he would eventually be able to generalize his approach to, three bodies which are mutually gravitationally acting on each other, and then to more than that there. And what I want to share is the approach that he took. All right. The story's told in June Barrow Green's book on Poincaré and the three-body problem. Right. Now, what Newton's laws and his law of universal gravitation, law of gravitation, what they do, they can be couched in terms of differential equations. That's equations involving rates of change. And the solutions of those equations is going to give you the motion of the bodies. And they're very hard to solve. And what Poincaré did was to develop methods for describing properties of the solutions of the differential equations without solving them. And this qualitative approach to differential equations is exceptionally important. And Poincaré's core idea was to explore the geometry or the topology of the solutions. And to do this, we need to introduce the notion of phase space. So suppose we have three particles. They're moving under gravitational attraction. Well, then, each particle has got a position and a speed. In order to specify its position, you need to give me the three numbers that tell me where it is, perhaps using Cartesian coordinates. And you need to give me three numbers telling me its speed in the x and the y and the z direction. So in order to specify the position and the speed of one particle, you have to give me three the three numbers that specify the speed and the three numbers that specify the position. Okay, and we've got three particles, so how many numbers do I have to have? I've got 6 for each of them, and 3 times 6 is going to be 18, isn't that right? Well, 3 times 6 is 18, that's certainly correct, but where it relates to it. So the position of the particle will correspond to a point in 18-dimensional space, right? And 18-dimensional space is just all the lists you can write of 18 numbers in a list. Okay, but quite hard to visualize. I'll give you that there. So it's a multi-dimensional space and called phase space. And here we have what Poincaré did. Now the black is what I'm thinking of as phase space. So this is the phase space of some system. And every position of the system corresponds to a point in that space. Now let's look and see what kind of behaviour you could have for the solutions. And what we're able to think of is that as the system evolves under its the laws that are governing it, we're going to get a trajectory. We're going to get a path in phase space. Every configuration of the system corresponds to a path, to a point in phase space. As the system evolves, we're going to get a path in phase space. Now, if it so happens that when you look at that path and follow it around, you return to a point where you've been before, you're going to have a periodic solution. Because once it's returned to somewhere that it's been before, it will follow the same path round and round. And what Poincaré did was to introduce a lower dimensional surface. If you can reduce the dimensions, in this case, it's very good. And that low dimensional surface is called a Poincaré section. And what he does is he starts the system off at different points on the Poincaré section. So here I'm starting it off at the point G. This is the green one. And it goes round, and it eventually comes back to the point G again. So if that is the behaviour, then you've got a periodic solution. Everything will come back to where it was, and in particular the thing will be stable because it's returned to where it was. But on the other hand, it may be that you started off at a point X, and when it returns, it's not to the point X, it's to another point, P of X, and then when it returns again, It's not to the point P of x, it's to another point P2 of x. All right? And what Poincaré wanted to do was to try to detect those loops that are for the green ones there, and to see when or not the thing returns, the point returns to its original position. Okay. Well, Poincaré found that for some situations, it did return to the point where it started, so that was good. They were periodic solutions, and the system was going to be stable. You know it's stable because it's returning to some position it's been at in the past, so it's just going to mimic its behaviour all over again. But then he found there were other solutions where it didn't return quite to where it was before, but it returned to a point on a small loop about where it was one before, and every time it came round, it took a small step around that loop. And that's okay, that's fairly reasonable behaviour, and Poincaré could deal with that. He could answer King Oscar's question about stability because he was able to say it's what its behaviour was. So he was awarded the prize. But while the paper was being prepared, and this is in June Barrows Green's book, tells you the story and the insight she's found out about it, one of the referees was unable to follow the arguments. And contrary to what Poincaré thought, even a small change in the initial conditions, Poincaré was using an approximation argument. He was saying if two trajectories start off from points that are quite close, then the succeeding behaviour will remain quite close. But that turns out not to be the case. And the results were not what he expected. What Poincaré had discovered was the basis of modern-day chaos theory. That even with deterministic laws, the resulting motion can be irregular and effectively unpredictable. And in particular, it has this sensitivity to initial conditions. It has this butterfly effect, as it's sometimes called. So let me summarise what I've said here. Key thing was to re-express the way you think of the problem. So instead of thinking of three bodies moving in 3 dimensions, you think of the system being represented by a single point, but in a higher dimensional space, phase space. Then you try to find Poincaré sections within this phase space and see whether or not, if something starts off in the Poincaré section, it returns to where it was. That would be a periodic solution. Or, slightly worse, but still manageable, if it doesn't return to the same point, but returns to some point on a small loop, and then takes steps around that loop as it comes back and forth. That's what's called a quasi-periodic solution. But unfortunately, things can get worse than that. They can get a lot worse than that there. And there are solutions, there are behaviour which are chaotic. So if you start the system off in 2 positions that are very close to each other, the trajectories will essentially subsequently diverge. So you're wanting to know, is the solar system stable or not? And this is work that was done published in 2009 in Nature by Jacques Lascar and Mikhail Gastineau from the Paris Observatory. The paper is called The Existence of Collisional Trajectories of Mercury, Mars and Venus with the Earth. And what they did was to use powerful computing techniques to simulate the evolution of the solar system over a 5 gigayear period. That's 5 billion years or 5,000 million years. And they took this time span because it's comparable to the life expectancy of the sun before the sun becomes a red giant. They used 2,501 scenarios. In each, there was a slight change in the starting conditions. So they might move Mercury by a metre. This is because of Poincaré's discovery that small differences can have a substantial effect. And what they found in these simulations was that in 1% of the solutions, it led to a large increase in Mercury's eccentricity, and an increase large enough to allow collisions with Venus or the Sun. And in one of those high eccentricity solutions, a subsequent decrease in Mercury's eccentricity induced a transfer of angular momentum from the giant planets that destabilizes all the planets that are closer into the Sun, and the Earth would end up crashing into, or Mercury, Mars or Venus end up colliding with the Earth to happen in about 3.34 gigayears, which is 3,340 million years from now. So as Ian Stewart says when he discusses it in this very nice book, The Great Mathematical Problems, in the chapter on orbital chaos and the three body problems, the answer to the question, is the solar system stable? Probably not. And Ian says, but we won't be around to find out. And that doesn't just mean us in this room, but what he says is that's going to be humankind. It's going to be mankind. So I think I find that simultaneously reassuring and deeply disappointing. So I've left time for questions this time, which was my plan. So thank you very much for coming along. You'll be able to astound and amaze your friends at your next dinner party talking about the solar system. And do come along for the Christmas treat for Euler's exponentials. Remember what I said last time, everybody goes away with a free exponential function. So thank you very much.